Now you might ask yourself how we can do this same kind of test but with a single categorical set of values and compare that against theoretical or expected probabilities. And we can, and that's called a goodness of fit test. And there's lots of examples for this. A perfect place to start is asking whether a roulette wheel or a pair of dice are fair. That is, if we compared the observed outcomes of the roulette wheel or the dice, do they match the expected values close enough? Now, it's not going to be perfect. Random chance is going to ensure that there is going to be some departure from perfect expected probabilities. So we're asking the question in terms of a hypothesis test. When you look at an example like babies' birthdays, we can look at, in this case, 3 different sets of samples. So we looked first at 50 random birthdays to see which day of the week they occurred on, then 300, then 1,300. And you might say it looks like some days are more common for birthdays than others. It looks like maybe Monday is a lot more common than Thursday. So we'll assume that in reality the chances of being born on any particular day is the same. That is 1/7. Let's calculate chi-squared and the probability, the p-value, for 50 randomly chosen children's birthdays. So we want the goodness of fit. So in statistics, we go down to goodness of fit. We've got, let's see, 7 columns. So let's make 7 columns. And I guess we could name them. I'll start this and return when I'm done. Okay, so here are the names of the columns. Now let's look at the observed count. So on Sunday there was 7, on Monday 11, on Tuesday 8, on Wednesday 9, on Thursday 4, on Friday 5, and on Saturday 6. So it looks like we have a total of 50 data points. Now, if this was independent, then each day would be equally likely. So we would be talking about 7/50ths each day. So let's get a calculator and divide 50 by 7. So it looks like we'd expect that many babies per day. So I'm going to paste that into each of these. Again, I'll see you when I'm done. And I'm about to paste in that last value, and when I do, here's our chi-squared value and our p-value. Notice that we can also ask to see the column percentages. So when we had the expected value, each percentage was the same, but it'll also give us the percentage for each of the observed values as well. And notice that this tells us that our chi-squared value is 4.88, and here's our p-value. We can then go through and do this again for the 300 randomly chosen baby birthdays and then the 1,300. And of course, see what happens with the p-scores. With our sample size of 50 babies, we got a chi-squared of 4.8 and a p-value of about 55.9%. Now, that p-value means that there's about a 56% chance of getting data, just like we did for those 50 babies, that actually correspond to the birthdays being equally likely from each of the weekdays. So in this first case with 50 babies, we'd say that there is insufficient evidence that the babies' birthdays are not equally likely on any day of the week. But we can be a little bit more sophisticated and we can see what happens when we get more data. So now let's look at 300 babies' birthdays. We now have a chi-squared of 5.62 and p is about 46.7%. Again, that could have happened simply by chance. But when we look at the data for 1,300 babies, we see something fairly remarkable. Now chi-squared is fairly large, 14.6, and p is much smaller. Now it's about 2.3% likely that we would have gotten data as extreme as that, given that babies are born equally on each day of the week. So we can say with 1,300 randomly selected babies' birthdays, we have evidence, where p is about 2.3%, that babies' birthdays were not uniformly distributed among the weekdays. We can perform so many tests with so much data that we can see a little bit more sophisticated analysis of that data. Let's look at another example, this one asking about the colors of M&Ms, a reoccurring theme in our book. The expected proportion can be found in the table. So this is what we're told the percentage of each of the colors is. So for example, if you look in the brown column, we counted out 371 out of the 2,620, but we were told that the proportion of M&Ms that are brown is 13%. And you can look at each of those columns to see the observed frequency and what we were expecting in terms of the proportion. We're asked to test at the 5% level to see if the observed frequencies actually support the claim that each of the colors occur in the proportions shown. So we're doing a hypothesis test. The null hypothesis is that the frequencies are consistent with the colors that we were told by Mars Corporation. The alternative hypothesis is that they are not consistent. Our level of significance alpha is 5%. Our first assumption is that the sample is random, but we're not told that this sample is random. Perhaps this case of M&Ms was in some way different. We're also checking that the expected frequencies for each of the colors is greater than or equal to 5. Let's go back and see that they're all at least 300, so we can be on the safe side there. Now we get out our calculator, put that data in, and we get our chi-squared, fairly large, 50.84. That tells us that p is going to be pretty darn close to 0. And so our conclusion is based on the fact that that p-value, really close to 0, is less than our alpha of 5%. So therefore, we can reject the null hypothesis. And that means that we say that there is enough evidence to show that the observed frequencies are not consistent with the distribution for M&M candies. That is, the distribution of colors is not what the company says.